Chase, and I work here in the Chemical Engineering Department at Northwestern University. And today I want to talk to you a little bit about how we can make the chemistry of our everyday lives a little bit cleaner using special tools called catalysts. So chemistry might sound a bit distant to you, like something that only happens in a lab setting. But you're probably familiar with a lot more chemical products than you might realize. For example, the clothes that you're wearing, the drugs you take, the plastics that you use, and even the materials in your car and phone are all products of chemical reactions. So where do these come from? All of these products started their journey to you as some kind of oil, like crude oil that we extract from the ground. This oil is then processed into raw chemicals, and these raw chemicals are then reprocessed, and that turns into the products that you all know and use likely every day. There's a little bit of a problem with this scheme, and that's here. Chemical manufacturing is extremely energy intensive, and it contributes significantly to greenhouse gas pollution and global warming. And in fact, it contributes to about 30%, or about a third, of the world's energy consumption. And to combat this, the chemical industry uses what's called a catalyst to reduce the amount of energy to make these important chemical reactions occur in about 85 to 90% of their processes. So let's go over a little bit about what that means. Up on the screen, I've shown a diagram known as a reaction coordinate. On the vertical axis, you can see the total amount of energy in our reaction system. On the horizontal axis, you can see the progress of a given chemical reaction. So this diagram generally shows us how much energy is required to make each step of a reaction happen. So we can begin with our reactants. We introduce reactants into solution, and these reactants can then come together to form a temporary transition state. But doing this requires a certain amount of energy input into the system. And this is known as the activation energy. And if this energy barrier, or activation energy barrier, is met, then our reactants can come together to form this temporary transition state, react, and separate to form our products. And this is a little bit of a problem because in order to meet this activation energy barrier, we usually have to input energy in the form of high temperatures or high pressures, which is usually done by burning fossil fuels. So of course that's generating a lot of pollution. And we can alter this scheme a little bit by offering a new path for a reaction to occur using a catalyst that forms a new transition state with a lower activation energy barrier. That might seem a little bit abstract, but you're probably familiar with some catalysts from your everyday life. For example, yeast is able to break down sugar into CO2 that makes your bread rise. So about 85 to 90% of these chemical processes are already using catalysts. What's the problem? Well, side products are a really big problem in industrial chemistry. If we take the reaction from our previous slide and we run it in an industrial reactor with a little bit more complicated solution, we add a catalyst, we can generate a lot of side products or unwanted byproducts. And when we do this, we then have to go through a series of separation steps to purify our final product, so we get rid of these byproducts. And doing this uses about half of the energy required in the chemical industry as a whole. So for a broader scale, that's about 15% of global energy going to just getting rid of all these unwanted byproducts. So you can see it's really important to control what our catalysts are making. It's kind of like when you're using yeast to break down sugar, you want it to form that carbon dioxide that makes your bread rise, and not the kind of ethanol you'd want to form if you were making beer. So this is where my research comes in. I study how we can use specialized porous coatings to control catalyst behavior. So I take catalysts, coat them with some kind of a porous coating. If we zoom in on one of these pores, you can see if the pore structure is just right, it will allow our reactants to come in and make contact with the catalyst surface, and these can then bounce off and form the desired products that we hope to gain out of this chemical reaction. But if one of our reactants is just slightly too large to fit inside the pore, we can prevent it from accessing the catalyst surface and therefore forming unwanted byproducts. So I study how we can tune the pore size to prevent these byproducts from happening. So to only allow the reactions that we want and not allow the reactions that we don't want. So doing this, I'm hoping we can cut down on the amount of energy required to go through those separation steps by preventing so many unwanted byproducts from forming. Therefore, we can make the chemical industry a little bit greener, as well as the products that come out of the chemical industry. So I hope this has given you a little bit of context as to where all these chemical products come from, and I'd be happy to answer any questions during the